You know, 15 minutes. Oh, that's 1 minute? Oh, I see. Now that's what it's like it's can. But it didn't seem to be, it seemed to go to sleep. Oh, that was his computer. Okay. I mean, presumably whenever I slide, it's reset.
Yeah.
So it should be fine. I don't think I'll have any slides after 10 minutes.
Yeah, I opened some windows already. I mean, as long as it's not crazy.
We should start quite early. And also if you're early on the item. Do you have my invitation?
we're just gonna have lunch and then change over drugs. No, I'm actually teaching course. My last teaching course.
How was it yesterday?
He didn't like it?
But yeah, but some of
You like it?
yeah, they are like
I like the interior of Changshu.
Here is better.
The atmosphere.
It's closer, that's the
I found the food very good.
Really confusing because the masters seem to casually put this relation, but it's not quite correct.
Well,
I think they're just using the
I have no comparison of the other.
masters suck. It's okay. Maybe some can be spaced out of it.
I think it's good, but the wine is a little bit too much.
That could be more expensive than a food.
Well, probably. But you know, I know Gucci more. Next time when you ask me, I recommend some.
I have a bottle of wine worth $3,000 US. You'll find special occasion I open it.
Very good, yeah. I can think of a few.
Well, we're about to finish the first conference. Okay, well, okay. Okay, what's it?
it's my great honor to introduce the first speaker today. Professor Richard Schoen is a professor at UC Irma and Stanford University and is currently the vice president of the American Mathematical Society. He will tell us about matrix of fixed area on higher genus surfaces with largest first eigenvalue.
Okay, well, let's see. Slow the wire up. Okay, well, I'd first like to thank Tristan and Yao for inviting me to this conference. It's always nice to come back to Boston. I'd also like to thank the audience for coming so early on a Sunday morning, so above and beyond the call of duty. So I'm going to describe today a problem, the type that I've been interested in for the last several years, but it's actually a very old problem. It has a long history, and it's a very, very elementary problem in a certain way, but there's still a lot that is not known about it. And so it's actually a global variational problem in that it's a matter of studying the eigenvalue, in particular, mostly the first eigenvalue, as a function of the metric. And so it's of course the eigenvalue is determined globally from the metric, and so it's a somewhat non-standard variational problem. And so I'm first going to talk about an old theorem. Actually, a lot of my talk is just going to survey what's known about this problem, and then in part 3 I'm going to talk about a new theorem which I have for high genus surfaces and some questions that are unresolved there. Okay, and so this is really a problem which is properly posed for general Riemannian metrics only on surfaces. And so we're going to take a two-dimensional real surface M, compact, smooth, and then if we choose a Riemannian metric on M, then we get its spectrum. So the lowest eigenvalue is 0, and then lambda 1, and etc. The subject, in a certain way, starts with an old theorem of Hirsch, Joseph Hirsch, from 1970. And Hirsch gave a very elegant proof of the beautiful theorem. Namely, he showed that if you take any smooth metric on S2, then lambda 1, the lowest non-zero eigenvalue times the area of the metric, is bounded above by 8 pi. And equality holds only for constant curvature.
It really starts by Sego. Sego did
Yeah.
what it is.
Well, Zego did it for
For
the
the unit.
disk, yeah, right.
I think the argument is exactly the same.
Well, actually, the method used in Hirsch's theorem is almost identical to a method used by Weinstock 15 years earlier, too. So there are some results for plane domains which certainly
But Sego did much
earlier than this.
Sego
But-
probably did much earlier.
Right, but I'm going to talk about closed surfaces here, so that's why I mentioned Hirsch first. Okay, and so let me just recall that the eigenvalues can be characterized variationally. So they're critical points of the Rayleigh quotient, which is this homogeneous of degree 0 quotients. The Dirichlet integral, these are for functions u on m. The Dirichlet integral divided by the square of the L2 norm, and then eigenvalues and eigenfunctions can be constructed by a variational procedure. Namely, the absolute minimum of this is 0, and it's achieved for the constant functions. And then we can look at, if we've constructed the first k minus 1 eigenvalues, then we can produce the kth one by minimizing the Rayleigh quotient over functions orthogonal to the first k minus 1 eigenfunctions. So that's a standard variational construction of them. And so in particular, lambda 1, which I'm mostly going to be interested in the talk, is the minimum of this quotient over functions that average to 0 on the surface. Okay, and so in Hirsch's theorem exploits some very special properties of the sphere. So let me first point out that that Hirsch's theorem is really about abstract metrics on the sphere. It's not about spheres embedded in R3. It considers arbitrary metrics. Now, the two basic properties of metrics that are used, and in fact no other surface has these properties, are the fact that, so the first one is that any metric is conformally equivalent to the standard one. We call G0 the standard metric on the unit sphere. So it's in the sense that given any G, there's a diffeomorphism of the sphere, so that the pullback of G is a function times G0 for some smooth function. The second property is that the sphere has a very large group of conformal transformations, and so in fact there are conformal transformations which blow up a neighborhood of a point to cover almost the entire sphere, and would shrink the complement to some other point on the sphere. So the Hirsch argument uses this conformal flexibility that the sphere has, and in fact no other surface has these two properties. Okay, and so let me mention another feature of the sphere which kind of leads into the question for other surfaces. So it's also true, of course, that the first eigenfunctions are the coordinate functions in the standard embedding. So in particular, the three first eigenfunctions, x1, x2, x3, have the property that the sum of their squares is 1. Now, if we have any compact surface, and if we have independent eigenfunctions, say u1 up to un plus 1, if we assume the sum of the squares is 1, then we can think of the map, capital U, which takes m into the unit n sphere. And in fact, this map is a harmonic map because the Laplacian of u is parallel to u because it's lambda times u. And so that means that the tangential part of the Laplacian is 0, and so that makes the map harmonic. And so that means the map also satisfies this harmonic map system. And so in particular, the square length of the gradient of u is constant, is equal to lambda. Now, if it happened that u were also conformal, then in fact the pullback metric, so if u were conformal and harmonic, then the pullback metric would be just 1/2 gradient u squared times g, and that's lambda over 2 times g. So in fact, u would be isometric up to a constant factor. Okay, and so so in other words, if we were able to construct a conformal harmonic map from a surface into a sphere by eigenfunctions, then that map is automatically isometric up to a constant factor. And so in particular, the metric is equivalent to the induced metric on the minimal surface. And so that suggests that metrics on minimal surfaces play a very special role in this problem. And so let me elaborate on that just a little bit. So now if I took a harmonic map from a surface into Sn, then if I take the component functions u1 up to un plus 1, then they are eigenfunctions for a conformal metric, 1/2 grad u squared. Because the harmonic map equation says that Laplacian ui is this. If I divide this by a gradient u squared, then I get the Laplacian for a conformal metric in 2 dimensions. And so whenever I have a harmonic map, these are eigenfunctions with eigenvalue 2 for this conformal metric. And in particular, if the map is also conformal, if it's harmonic and conformal, that means it's a minimal immersion, then these are eigenfunctions with eigenvalue 2 for the induced metric. Okay? And so the Hirsch theorem leads to the corresponding question for general surfaces. So you can ask, given any compact surface, can we find a metric, a smooth metric on the surface, say of a fixed area, which maximizes the lowest non-zero eigenvalue? And so if so, what's its geometric structure? So one of the reasons I got interested in this problem is that it turns out that if these metrics exist, then the extremals are very nice geometric objects, which in fact they're based on the previous 2 slides, you might guess that they're actually minimal surfaces in spheres. Okay, and so in particular, we could look at the question for the torus or for higher genus surfaces, or for non-orientable surfaces as well. Okay, and so there's a general theorem which is due to Nadarashvili in about 20 years ago, 1996, which gives a characterization of maximizing metrics. So if you have a smooth metric which maximizes, then in fact the multiplicity of lambda 1 is always at least 3. So it's relatively high multiplicity. So you in general expect the maximizing metrics to be sort of the nicest ones in the sense that they should have relatively high multiplicity. And so this verifies that the multiplicity is at least 3, assuming the metric exists. And in fact, there are independent eigenfunctions, u1 up to un plus 1, the sum of whose squares is 1, and so that the map is a conformal map to the unit sphere. So in other words, what it says is that if we can actually maximize this problem, we can solve the maximizing problem, then we will be able to arrange eigenfunctions which give us a minimal immersion into the sphere, and the metric itself is then the induced metric on that surface. So we can understand the metrics as induced metrics on minimal surfaces in spheres. Okay, and so this is the general result about maximizing metrics, assuming they exist. So I'm going to explain a little bit about how why the theorem is true. But let me just say a little bit about minimal surfaces first. So minimal surfaces have come up in several previous talks, but they're surfaces that locally minimize area. So they arise as soap films, and they're characterized by the condition that their mean curvature is 0. So I have some pictures here. So this is a soap film bounding a curve. These are minimal surfaces in R3. This is the catenoid, rotationally symmetric surface, and this is a minimal surface in R3 with 3n. So there are lots and lots of minimal surfaces, and it's, again, minimizing area is one of the oldest and most classical variational problems in geometric analysis. And so this eigenvalue consideration leads to a slightly different way of looking at certain classes of minimal surfaces. And so that's another reason that I got interested in it. Okay, and so let me just say a little bit about why minimal surfaces should arise as eigenvalue extremals. I don't have time to go through the proof of the thing explicitly, but let me just say that the condition that a map U from M to a sphere is a minimal immersion is that the component functions u1 up to un plus 1 satisfy two conditions. So the first condition is the sum of the squares is 1, and the conformality condition we can write as a condition on which is quadratic in the first derivative. So this is uxi, which is a vector in Rn plus 1. This is the dot product, and then minus 1/2 this is just the trace part of that. So it's the condition that the trace-free part of the uxi dot uxj is 0. So that's the conformality condition. And so it turns out that each of these two conditions arises from as a variational condition when the metric is varied sort of in the two distinct ways. So natural ways to vary a metric are in the conformal class. So you could do a variation that preserves the conformal class. You just multiply it by a function. And this first condition it comes out of variations of that type. And the second condition comes out of variations of the metric which are orthogonal to those. So they're metrics which preserve the area form, if you like. So you can think of the metrics that preserve the area form, but are non-trivial deformations. So those give rise to this second condition. Now, on the other hand, you can ask, well, why are there n plus 1 functions there? How does that come out? Well, the reason for that is because the other problem with this eigenvalue functional, is that it's not a C1 function on the space of metrics. So if you vary the metric in a smooth way, an eigenvalue like lambda 1 doesn't necessarily vary in a C1 fashion, and that's because of multiplicity problems. So you can roughly think of the eigenfunction as the minimum of a finite number of C1 functions. So what can happen is that you can have, so if you think of a family of varying metric GT, so you have here's G0, then you could have two eigenfunctions that cross. So here this might be lambda 1, and this might be lambda 2, but here this becomes lambda 1, and this becomes lambda 2. So lambda 1 is not smooth. It's a Lipschitz function in general. And so the reason for the reason that you get a family of eigenfunctions is because of this multiplicity issue. And so in fact, the way that comes out is it's a convexity argument, actually a very clever argument, I think, which was I first saw in Nadarashvili's paper. And so it's the critical condition, or the maximizing condition, yields a collection of eigenfunctions so that when you sum up the corresponding first variations, you get 0. So let me now just describe some known results on this problem. Well, we talked about the Hirsch theorem on the sphere, and so the Hirsch theorem, if you like, says that the constant curvature metric is the unique maximum on the two-sphere. However, what we know about minimal immersions of two spheres into n spheres suggests that this is not the whole story for S2. In fact, there are many other minimal immersions of S2 and Sn where the component functions, the embedding functions, are higher eigenfunctions. So you can find them. Actually, you can find them where the embedding functions are lambda k for any choice of k. You can find such immersions. There's a rather rich theory of minimal immersions of S2 and Sn for n bigger than 3. And in fact, there's at least roughly a classification by what are called interval systems methods. And so this suggests that the higher eigenvalues should also have critical points in the space of metrics. However, it's known rigorously. I mean, I would expect that in fact for higher eigenvalues you can never maximize them. The maximum probably never exists. In fact, that's known rigorously for lambda 2, which is the theorem of Nadarashvili. So it's natural to try to explain this class of minimal immersions by min-max or maybe max-min methods on the eigenvalues. So although you expect the higher eigenvalues to have critical points, you don't expect them to be maximizers. So you need some more subtle method to construct those, assuming they can be constructed by variational methods. Actually, from the point of view of area, I don't think there's any explanation of the minimal S2s and Sn from a variational point of view. Of course, minimal surfaces are also critical points of the area, and again, they also never minimize area. So you could try to understand them in terms of min-max methods, but really only the very simplest ones can be understood in that way. So in particular, this class certainly can't be. So there may be more interesting results even for metrics on S2, I think. The next case that was handled is the real projective plane, and this was done by Li and Yao in 1982, I think. And in that case, the constant curvature metric turns out to be the unique maximum. So if you fix the area and maximize lambda 1, it turns out that the constant curvature metric does that. And so what Li and Yao used to prove that is two things. So first of all, the fact that there's a very, very natural minimal embedding of RP2 into S4. So classical embedding is called the Veronese surface. So it's actually a minimal immersion into a sphere by second eigenfunctions on the two-sphere. And so these are, since they're second eigenfunctions, they're actually first eigenfunctions on the quotient on RP2. And so these are, of course, harmonic functions, and if you work it out, the sum of the squares is 1, and it's a conformal map. Okay, and so in fact, Li and Yao actually proved a much stronger theorem. They proved that whenever you have a minimal immersion by first eigenfunctions, then the induced metric on that surface actually maximizes lambda 1 times the area in its conformal class. Okay, so generally, whenever you can find a minimal surface in the sphere embedded by first eigenfunctions, then that metric will have the special property that it maximizes in its conformal class. And the special thing about S2 and RP2 is that there's only one conformal class, and so that's why. So it's sufficient to exhibit by first eigenfunctions, then that one will automatically maximize. And so that's the reason it works here. Now other surfaces will have families of distinct conformal classes, and so it's not enough. Even if you construct a minimal immersion by first eigenfunctions from some torus, say, you don't know that that maximizes because there may be some other inequivalent torus which does better. So that's the difficulty in the problem. Okay. On the other hand, the torus case has been handled, although it turns out to be a lot harder analytically. And so it turns out that for the torus, there's the maximizer can be explicitly determined. And so this paper of Nadarashvili that I referred to earlier. So it turns out that the best, the optimal torus is a 60-degree rhombic torus. So it's the most symmetric torus, if you like. So its periods are 1, 0, and this is a unit vector with an angle of 60 degrees. And so the corresponding embedding by eigenfunctions I've written in complex form here. So this goes into C3, which is R6. And so this is a flat minimal embedding. So it turns out to be the induced metric is flat, and it's embedded by first eigenfunctions on that. And so just roughly the way that goes is there's first a difficult theorem, which is the proof that some maximizer exists. So there's a maximizer which is sufficiently smooth, which exists. So it's first constructing by analytic means, and I'm going to discuss this later in the talk for more general for higher genus surfaces. And so once you have a maximizer, then it produces a minimal immersion in the sphere. There's a result by Montiel and Ross which asserts that these surfaces embedded by first eigenfunctions have a rather amazing property. Namely, whenever you have a conformal symmetry of the surface, that is a conformal diffeomorphism of the surface, that map is actually an isometry, so it preserves the induced metric. That's true. Actually, there's one exception, which is the equatorial two-sphere. So the equatorial two-sphere doesn't have that property. But any non-trivial minimal surface embedded by first eigenfunctions does have that property. And so in particular, if we have a torus, then of course it always has a transitive group of conformal transformations, and so it becomes homogeneous, and so it's flat. So the torus has to be flat. And then it turns out that flat minimal tori in principle can be classified, and it's known that there in fact are only 2 flat minimal immersions of the torus into a sphere by first eigenfunctions. So actually there are infinitely many if you take higher eigenfunctions, but there are only 2 by first. There's the Clifford torus in S3, which might have been your guess as to the maximizer. It turns out it's not actually the maximizer. There's the second torus which goes into S5, and that one turns out to have larger areas. So in fact, it beats the Clifford torus. So that settles the torus case. Now the Klein bottle case, that's a surface which is double covered by a torus, was also resolved through a series of papers, so by a number of authors, which I've listed here. And it turns out one maybe interesting aspect of this case is that the extremal metric is actually not flat. So the Klein bottle, unlike the torus, doesn't have a transitive group of conformal transformations. It only has an S1 action, and so you get S1 invariant metrics, and this problem was analyzed by these authors. And again, the idea of the proof is similar. You prove by general principles that the maximizing metric exists, and therefore it's S1 invariant. And then it's a matter of understanding the ODE. ODE is involved. Okay, so that's the Klein bottle. So and again, in principle, it's understood. Now, if you look at the question for higher genus surfaces, genus 2 or higher, say orientable or non-orientable surfaces, then in fact not very much is known about the maximizers. There are, however, remarkably good upper and lower bounds in terms of the genus. And so if I'm calling gamma the genus of the surface here, and I'm defining lambda star of gamma to be the supremum of the area of lambda 1 times the area taken over all smooth metrics on the surface. Call that lambda star. And so there are upper and lower bounds I've written here. And you notice they're both linear in the genus. And so the upper bound is an old theorem of Yang and Yao. And it uses an extension of the Hirsch method where instead of a conformal diffeomorphism, it uses a branch covering. So that number there, gamma plus 3 over 2, that's the integer part, gamma plus 3 over 2. It turns out, it comes from Riemann surface theory. It turns out to be the smallest degree of such a branch covering, which works for all surfaces of genus gamma. So it gives you an upper bound which goes for gamma large like 4 pi gamma. Now the lower bound is it actually comes from another area. It's so to get a lower bound, since we're maximizing, it's enough to find an interesting surface as a competitor, as a comparison. And so what we want to do is find a surface whose area is known and whose lowest eigenvalue is not too small, right? So you want to construct a surface where lambda 1 is relatively large, and that actually is done using number theoretic techniques. So there are certain surfaces which are arithmetic. They come from arithmetic lattices, and those surfaces have remarkably large eigenvalues. Particularly, the lowest eigenvalue is actually bounded below by a fixed constant, 3/16, which has actually been improved a little bit. The conjecture is 1/4 for this. And so the lower bound there has gotten, that number is just 3/16 times the area of a hyperbolic metric on a surface of genus gamma, which is given by the Gauss-Bonnet theorem. Okay, and so the lower, there's also a lower bound which is linear in gamma. It goes like 3 pi over 4 times gamma. Okay, and let me just say that in genus 2 there's a conjectured maximizer, and it's conjectured by, it's in a paper published in 2006, I think, by these 5 authors, it exhibits an explicit metric on a particular surface of genus 2, which is conjectured to maximize lambda 1 for its area. And there's some evidence given there. Actually, one of the authors is a numerical analyst, so there's numerical evidence given for this. But I don't think it's been rigorously shown that this metric actually maximizes. And so what it is maybe a slightly strange minimal surface. Namely, one possibility in this problem is that the maximizing metric, assuming it exists, is just given by a branch covering of S2. Right? So generally, a conformal minimal immersion may or may not, it could be of codimension 0, so it might go into S2. And in fact, that's the conjectured form of this metric. So it's conjectured to be a twofold branch covering of S2, and it's from a very special surface of genus 2 called the Bolzа surface, which actually arises in some other extremal problems in geometry. But so as a metric, it's actually a constant curvature 1 metric. So its curvature is 1 except for cone points. So there's six cone points of cone angle 4 pi. And so again, the component functions are eigenfunctions. And so the whole question in trying to rigorously verify this conjecture would be to check that the eigenfunctions are first eigenfunctions. They're eigenfunctions with eigenvalue 2, but the question is, are they first? And in fact, the authors give numerical evidence that should be the case. But actually, I didn't believe this conjecture for a long time, so I had my own numerical analyst do this. And in fact, he came up with more or less corroborating evidence from a slightly different point of view. So I do think that this is probably right. Although it's a little bit of a disappointing answer for a minimal surface guy like me, because after all, a codimension 0 minimal surface is, could put you to sleep, right? So there's another way to state the conjecture is that the upper bound, the Yang-Yao upper bound, which of course arises by considering branch coverings of the sphere, is actually achieved in the genus 2 case. So that means that lambda star of 2 would be 16 pi in this case. I should point out that it turns out that hyperbolic metrics never realize these extremals. So in fact, a hyperbolic metric can't be even locally minimally immersed into a sphere. So the lower bound is never sharp, but the upper bound could be sharp for certain values of the genus, and the conjecture is that it in fact is sharp for genus 2. Okay, and so in this last part of my talk, I want to describe a new theorem about the construction of maximizing metrics, and it resolves a few issues, but it still leaves open very many questions. And so basically, in order to construct a maximizing metric for this problem, it's a matter of, if you do it variationally, you can think of taking a maximizing sequence of metrics and then trying to take a limit of that sequence. And so basically, when you consider metrics on a surface, there are two things that are important. So one is the conformal structure, which is defined by the metrics, and so it turns out that the space of conformal structures, the space of metrics, of course, is an infinite dimensional space, but the space of inequivalent conformal structures up to diffeomorphism is only finite dimensional. Okay? And so controlling the conformal structure in a certain sense is a finite dimensional problem. And then the second part is maximizing within a fixed or a compact set of conformal structures. Okay, so in other words, if we want to take a limit of our maximizing sequence, the first thing we would like to know is that the conformal structure doesn't degenerate. Okay, and then it's a question of we're working in essentially a fixed conformal class, and then it's a problem of achieving the maximum in the class. And so actually there's a lot of work on the second part of this. In particular, there's a recent work of Petrides, and also there's work of Nadarashvili and Sear on the second part. And those works actually resolve the second one. So if you fix the conformal class, then you can maximize. In fact, I'm going to describe it briefly in the next slides. And then what I want to announce in the talk is the solution of the first one, controlling the conformal structure. Okay, and so actually maximizing in the conformal class is also quite an interesting, quite a subtle thing. If you fix a conformal class of metrics, you can always, so we're working on surfaces of genus at least 2, so we can mark our conformal classes by constant curvature metrics. So we can always, in any conformal class, choose a metric G naught which has constant negative curvature. So it's a hyperbolic metric. And then if we choose any measure mu on M and say it's absolutely continuous with respect to the area measure mu0 of G0, then we can write it as e to the 2v times mu0, and then this e to the 2v defines a new conformal metric. And so you can really think of the eigenvalue as a function of a measure. Okay, so we can think of lambda 1 of mu. So given any measure which is absolutely continuous, you can then, and let's say we take probability measures, so we have the area normalization, so we assume the total measure is 1, then it's a problem of maximizing lambda 1 of mu over measures mu. So one of the subtleties about the problem, of course, ultimately this problem is related to harmonic maps and minimals, or actually the conformal problem is related directly to harmonic maps. And so the regularity for the ultimate metric comes from the condition that it can be written in terms of eigenfunctions. So that's the subtle thing. And so somehow when you do the existence procedure, you have to sort of simultaneously construct the eigenfunctions. Otherwise, you won't be able to get much information about the metric. And so one thing that would first come to mind here is, why don't we know that the space of measures is compact in the weak star topology, so we could just take a weak star limit of a maximizing sequence and we produce a limiting measure. The problem is that limiting measure will not generally be absolutely continuous, and it may not even have discrete spectrum. If you consider you can certainly find singular measures where the eigenvalues don't even exist, and so it's a bit of a problem to get the regularity of that. In fact, it's not even clear that the supremum is the same if we allow singular measures. And so that may sound like a technical problem, but actually, if you took a measure which is something like the arc length measure on a curve on the surface, then when you do the eigenvalue problem, you get a different eigenvalue problem. You get an eigenvalue problem which is related to the Dirichlet to Neumann map. It's a Steklov type eigenvalue problem. So in fact, if you consider singular measures, you're actually including some rather different eigenvalue problems. And the fact that the one for smooth measures should maximize is not obvious by any means. And so because of that problem, the procedure for constructing the maximizing metric involves a regularization procedure. Okay, so the idea is not to just take a limit of a weak star limit of measures, but to look at a regularization procedure and construct a special maximizing sequence of smooth metrics where we have good control on the eigenfunctions. That's the basic idea. And so, in fact, so Nadarashvili did something like that in the torus case, but in a rather complicated way. So I actually initially worked on a related problem for surfaces with boundary and with Ilana Fraser, and she and I developed an existence procedure for the maximizers, which has a direct analog for closed surfaces, and in fact it gets around some of the technical issues that occurred in the Nadarashvili approach. So the idea is that so the regularization procedure goes like this. So we exploit the fact that we're in a given conformal class, so there's a good background metric G naught, and so it has a heap kernel, so K of x, y, t. And so for any positive epsilon and any measure on M, we can smooth the measure. We can consider mu epsilon to be the solution of the heat equation at time epsilon, starting with initial measure mu, and then we multiply that times the measure mu0. So the advantage of this regularization is that it's completely geometric. In other words, it doesn't depend on any choice of coordinates. If you apply a diffeomorphism, then the regularization goes over in a natural way. So then it's very easy to solve the regularized problem. So if you maximize over, the mu epsilons are really compact in any smooth topology, and so it's easy to maximize the problem for a fixed positive epsilon, and then it comes down to a question of limits of critical points. So it turns out that the maximizers for the approximate problem have some, of course they're not given by harmonic maps or minimal immersions, but they're sort of, their eigenfunctions have some special properties, and I don't have time to go into it, but you have enough control on them to show that you can in fact construct maps from the eigenfunctions which converge uniformly. So it's important to have the strong enough convergence to a map which is continuous and harmonic, and then the higher regularity comes from harmonic map theory. And so that's roughly the idea. So it's a rather I think unusual variational problem, even in even fixing a conformal class. Okay, and so I want to talk now about the problem of controlling the conformal structure. Okay, and so we assume we have a compact surface of genus bigger than 1. Okay, and then so again, given a metric, there's a unique hyperbolic metric in the conformal class. So we write it in this way. Okay, and so we think of the G naughts as marking the conformal class. Okay, and so in order to show the conformal class doesn't degenerate, what we have to show is that we need to prove a lower bound on the injectivity radius of G naught. So when the conformal class degenerates, you get a neck pinch. So you get the hyperbolic metric in that class will have a short closed geodesic. Okay? And so that's the only way that the degeneration can occur. And so we have to understand why that can't happen. We have to understand that issue. Let me now state the main theorem. So again, remember that lambda star of gamma by definition is the sup of these lambda 1a over smooth metrics. And then the idea, so the idea of proving the existence for a given genus gamma is you try to show that if you have a degeneration, then in fact lambda 1 is near that of the surface of lower genus. So you pinch a handle and you converge to a surface of lower genus. And so it turns out to be enough. There's a little bit of work here. Actually, this is also discussed in Petrini's paper, but something very similar is in my paper with Fraser too. So so what would happen is if you have degeneration, is that there would be some lower genus gamma 1, lower than gamma, so that lambda star is bounded above by lambda star of gamma. Okay, and so if we knew that the lambda stars of gamma were strictly increasing, then that would be enough to rule this out. And so that's the theorem I want to describe. It's called the Handel. I'll call it the Handel addition theorem. So assume the gamma is at least 1, and let's assume that lambda star of gamma is achieved. So assume there's a metric that achieves that one. Then the claim is that when we can add a handle and we get a larger value of lambda star. Lambda star of gamma plus 1 is strictly bigger. So let me just say that it's much easier to show the weak inequality that lambda star of gamma plus 1 is greater than or equal. It's relatively straightforward. It's just a matter of constructing a metric where the handle is negligible from the eigenvalue point of view. It's actually a special case of the theorem of Colbois and Elsevier. And so the issue here is to get a strict increasing property for the eigenvalue when we add a handle. And so let me point out some consequences of the theorem first. So the first consequence is, and again based on the other work that I described, is that for any genus bigger than 1, there is a maximizing metric on a surface of genus gamma. It's a smooth metric with possibly a finite number of cone points, as you would expect. Okay, and so this follows by induction. So you can start even with the sphere, but we know the torus, and so when we add a handle, we know that the torus is achieved. So when we add a handle, we get that for genus 2, it's strictly bigger. Lambda star is strictly bigger, and so we can rule out degeneration, conformal degeneration for genus 2. So we prove existence there, and then we prove it inductively up to arbitrary genus. Okay. So remember that the cases that we described, in the torus case, the problem, the maximum was achieved by a rather high multiplicity metric that went into S5, whereas the conjecture in the genus 2 case is that it's actually achieved by a branch covering. And so, I mean, my naive guess is that the maximizer is almost never achieved by a branch covering. In fact, you might conjecture that the maximizer would have multiplicity which tends to infinity with the genus. So in other words, the sphere that you go into, the dimension should go to infinity as the genus goes to infinity. Now we don't know that at all, but the theorem does imply something in this direction. Namely, it implies that for gamma odd values of the genus, the upper bound is not achieved, the upper bound. So in other words, it's not achieved for genus 1. It conjecturally is achieved for genus 2. For genus 3, it's not achieved in general for odd genus. And the reason for that is straightforward. So the multiplicity there would be at least 4. And so it follows because the upper bound that we gave, the Yang upper bound, doesn't increase when we go from an odd number to the next number, the next even. And so if it were achieved for an odd number, then the upper bound would be the same for the next even number. But we proved that the upper bound actually, the lambda star actually goes strictly up, and so this is not possible. So if we're achieved for gamma, then it would have to be achieved for the next even number as well. But that would imply that there's no jump in the upper bounds don't jump. They're constant from odd to even, and so it says something about the multiplicity, but of course it's much weaker than one would like. And so let me just describe roughly what goes into this proof. It's some interesting constructions for special kinds of handles. So remember, we get a surface of genus gamma plus 1 from a surface of genus gamma by adding a handle. So these are some pictures of handles. So I could take, I add a handle by removing two discs and putting in an annulus circle across an interval, joining them. And so these are some pictures of handles. It turns out the shape of the handle, in other words, what geometry you put on the handle, it plays a key role here. And so, for example, if we took our handle to be a flat handle, which is quite long, and then if we shrink the radius, the cross section of the handle to 0, keeping the length the same, then what will happen is that the lowest eigenvalue will actually go to 0. Right? So a long, thin cylinder is going to have a small eigenvalue, and so when we do that shrinking, the lambda 1 will actually converge to 0, and so the first eigenfunctions for the genus gamma plus 1 surface will concentrate on the handle. So if you arrange there are two kinds of sort of extreme behaviors which can occur, and which one does occur depends on the geometry of the handle. One possibility is that the lowest eigenvalue for the higher genus surface, one possibility is the eigenfunction, the lowest eigenfunction concentrates on the handle. So it actually goes to 0 on the original surface and blows up on the handle. And that would happen, for example, if you chose a handle which is too long and thin. The other possibility is that the handle's sort of negligible and the lowest eigenfunctions actually converge to a lowest eigenfunction on the original surface. And so again, which of those occurs depends on the geometry of the handle. And so the goal is to add a handle in a very delicate sort of way so that we can understand what's going on. And so what we need to do, of course, remember that the lambda star is the maximum, right? So all I have to do is exhibit one metric, g hat, I'll call it, on a surface of genus gamma plus 1, where the product, lambda 1 of g hat times the area, is strictly bigger than this, because I'm assuming this one achieves the maximum already at genus gamma. Okay, and then it would follow, because we're maximizing, that we have strict inequality. Okay, and so the idea is, so we're going to get the increase in the following way. We're going to construct a metric g hat on a higher genus surface whose area is just a little bit bigger than the area of g, bigger than the one we started with. And we're going to do it so that there is a normalized first eigenfunction, so normalized L2 norm is 1, for g hat, which is very, very small on the handle. So the idea is we're going to arrange things so we can find an eigenfunction which is quite small on the handle. And so just imagine in a extreme case that we had an eigenfunction which was actually 0 on the handle. So if it were 0, then we could prove that we could then just extend it. We could remove the handle and we could extend it as a test function on the original surface. We would end up proving that the lambda 1 for the original surface is actually smaller than lambda 1 for g, because lambda 1g is the infimum over those things. So if the eigenfunction is actually close to 0 on the handle, then we'll be able to show that the eigenvalue lambda 1 doesn't go up by very much. And so, sorry, it doesn't go down by very much. So it's bigger than or equal to the lambda 1 of g minus a small enough constant, so that when we multiply the two together, lambda 1 of g hat times the area, we get a strict increase. So that's going to be the idea. So we're going to construct a very special geometry for the neck so that we can achieve this property. Okay, and so the idea is to use hyperbolic cusp necks. So we're going to use very special geometry on the handles, so we're going to take our metric. It'll be a piecewise smooth metric, and it will be of constant negative Gauss curvature, where we're going to choose the curvature kappa correctly. We're going to make a proper choice. Okay, and so the picture is like this. We're assuming that we have. So both of these circles are supposed to be very short. So the size of the bigger circle is of order epsilon, and the smaller one is of order delta. And delta is going to be chosen much, much smaller than epsilon. So we're going to take so these are constant negative curvature metrics, which can be explicitly written down. And they have the property that the base circle has length epsilon and the top circle has length delta. And I can make delta go as small as I want with a fixed epsilon in these metrics. And then I'll think of attaching the tops. So I'll just put together the two top pieces. I'll get a piecewise smooth metric. And then the important point is to understand the radial eigenfunctions on the neck. And so we're gonna be able to construct eigenfunctions which are small because their radial average is small. So we can think of taking an eigenfunction. So the neck, of course, has an S1 symmetry. So if we take an eigenfunction just on the neck, and we not necessarily radial, if we can average it on the circles, and we'll get a radial eigenfunction. And so if that radial average is identically 0, that will make the eigenfunction very, very small. And so the idea is to produce a situation where we can get an eigenfunction whose radial averages are 0. Okay, and so the key thing about these necks, in fact, we can explicitly describe them. I don't have a picture here, but they're so we can write them as metrics in the upper half plane. Describe it here. So we think of the upper half plane. And then we have the hyperbolic metric of curvature minus kappa. So that would be 1 over kappa. Y squared dx squared plus dy squared. And then we're going to identify under a short translation. So we're going to make it so that at height 1 here we get a base circle of radius of size epsilon. So this will be this distance is epsilon times the square root of kappa. And we think of identifying these two sides. So this is the picture that cuts. We take the part up here and we identify the two sides, and then we go up here to a certain value. So this gets shorter and shorter as we go up, and we go up high enough so that this y naught is on the order of epsilon over delta. So if we choose delta to be very small, then that'll be high up on the picture. And so this is the conformal picture of our neck. Now the key thing about these metrics is that the radial eigenfunctions, of course, can be explicitly written down. And so one of the reasons I didn't take a hyperbolic metric on the whole annular region is because it's a little harder to write down the eigenfunctions. But in this picture, the radial eigenfunctions are explicit. So they're of the form y to the p, where and the eigenvalue is kappa times p minus 1. So in general, we're interested in lambda positive. So in general, p is between 0 and 1, and we can look at y to the p. So that gives us a radial eigenfunction, and there's the radial eigenfunction with the given eigenvalue. And now typically what happens is one of these eigenfunctions. So what the key property we need in order to make this work is we need to understand the concentration of the eigenfunctions. Okay, and so the question of whether an eigenfunction will concentrate or not depends on whether it's in L2 or not on the infinite annulus. So if we look at the eigenfunctions and we ask whether they're in L2, then for most choices of p, one of them is in L2 and the other is not in L2. So the one with p smaller, because the L2 norm. So when this is 1 over y squared is the area form. So when I square, so typically in order to be an L2, p has to be strictly smaller than a half, and so usually one of them's an L2 and the other's not. Now there's a special choice of p, namely the midpoint, p equals a half, where both eigenfunctions, and in fact you can check that any linear combination also has the same property. that they're both not in L2 on the infinite cusp. So if I send y naught to infinity, they're not in L2. So that means every radial eigenfunction will blow up, will not be in L2. And so in particular, if I normalize the eigenfunction to have L2 norm 1, when I go up high, it'll be very, very small here, almost 0, and it'll be concentrating on the neck. That's the basic idea. So the idea is to get eigenfunctions which do concentrate, but then to control the eigenvalue. Okay, so in other words, there's a special eigenvalue which is kappa over 4 for metrics with curvature minus kappa, where all of the radial eigenfunctions on the cusp concentrate. So that's the key thing. Okay, and so so in particular, if I look at the original surface, so I think of adding my handle now. So I have the original eigenfunctions. So I have the eigenfunctions on the original surface. Now, when I do this handle addition, those eigenfunctions will still essentially be there. There will be eigenfunctions which are very, very close to those eigenfunctions on the original surface, and small on the neck or controlled on the neck, small L2 norm, and those will have eigenvalue very close to lambda 1. Okay, and so I get this picture where I have the eigenfunctions which don't concentrate, and their value is approximately lambda 1. Their eigenvalue is approximately lambda 1, and I have ones which do, and their eigenvalue is approximately kappa over 4. And so the idea is to make these two guys equal. Kappa over 4 is lambda 1. So we adjust the curvature of the neck so that kappa over 4 is lambda 1. And what that tells us is that we can do a linear combination. So we can take one of our eigenfunctions that doesn't concentrate, and we can subtract off its radial average. See, its radial average will be a radial eigenfunction on the end, and we know that those do concentrate. So we can take a linear combination, and we can make the radial average 0. Okay? So there's a slight, there are some technical issues in this, but the basic idea is that you get an eigenvalue, or an approximate eigenvalue, which is approximately the first eigenvalue, which has multiplicity 3. So it has these two radial eigenfunctions plus at least one non-concentrating eigenfunction. Then you can take a linear combination to get a first eigenfunction which has zero averages around the circles. Okay, and so that turns out to be small enough. You can then argue it's small enough to carry through the argument. So that's the idea. So it's a very delicate adjustment of the neck to do that. Okay, and so that's a summary of the proof, way it goes. And so I should say, by the way, this idea actually comes from the work we did on surfaces with boundary, because there's a kind of analogous theorem where we had to show that when you add a boundary component, again, the eigenvalue doesn't go down too much. In that case, it was a Steklov eigenvalue. And so there's a very similar idea that goes into that. This is a little bit more complicated than the one there. Okay, so let me just finish up with a couple of slides here on open problems. So again, we discussed the problem of understanding the maximizing metrics on a smooth compact surface that maximize lambda 1 fixed area. And so, of course, one open problem that I mentioned is the genus 2 conjecture. It would be nice to give a rigorous proof of that. Then the question of whether the Yang-Yao upper bound can be achieved for any values of gamma bigger than 2, certainly important. And then, of course, the asymptotics of lambda star of gamma would be interesting to understand. So what's the right value of lambda star of gamma over gamma? There's some connections with questions about minimal surfaces that I want to just point out in the last slide. And so the lower bound was a kind of mysterious thing. It came from number theory. So it'd be interesting to do that more geometrically. And actually, there's a large class of metrics that one could consider, namely the embedded minimal surfaces in S3. So the Lawson surfaces, of which there exists one of every genus, are known to have the lowest eigenvalue 2. So lambda 1 is 2 for those. And so you can ask, well, how large can the area be? And so if you take an embedded minimal surface in S3 of genus gamma, then its area is bounded above by something linear in gamma. On the other hand, the maximum area of the Lawson surfaces actually goes something like square root of gamma. So if you look at the construction there, you can never really get up to gamma. And so in particular, I think it may be true that the maximum area of a minimal surface in S3, possibly a minimal surface in Sn for a fixed n, say with lambda 1 equals 2, that the area is little o of gamma. So if you could prove that, it would imply the multiplicity goes to infinity. So the question of whether the multiplicity goes to infinity or not, it can be handled. In fact, it's roughly equivalent to the statement that the areas don't grow too quickly. And I think that's a very interesting question, both from a minimal surface point of view and, of course, from the eigenvalue point of view. It's also related to how many small eigenvalues you can have. So if you take say an embedded minimal surface in S3, then let's say lambda 1 is 2, then the question is how many eigenvalues can there be up to a fixed constant? And so, of course, asymptotically we know something about that from the Weyl embedding, or the Weyl asymptotic law. But for example, if you could show that the gammath eigenvalue, so if you look at a constant times gamma, if you could show that the gammath eigenvalue actually grows with gamma, grows independently of the surface, it gets bigger than anything that goes to infinity, then it would imply this kind of statement. So understanding higher eigenvalues for embedded minimal surfaces is very much related to this question. So there are a lot of interesting questions, particularly. I mean, for higher genus, it's not going to be possible to actually classify the solutions, but I think there should be good asymptotic information that one can obtain. Okay, so I'm finished.
Any questions?
Instead of using genus, use the degree of the surface onto a sphere. It's probably better.
The degree onto
conformal.
the conformal volume.
Yeah, you can say conformal. There probably is a better parameter in the genus.
Well, I mean, I think that this problem is equivalent to determining the maximum conformal volume over all conformal structures, right? So,
Well, in a way, but so in my field review,
yeah.
you take degree is actually smaller sometimes than the genus.
Mm-hmm.
So
Oh, I see. You mean there are special conformal structures where the degree is small, yeah.
Is actually very
Right,
small.
right.
For example,
Hyperelliptic, yeah.
hyperelliptic.
Right. Mm-hmm.
So I think in the case of two-dimensional degree may be a better parameter than genus.
Well, the degree, though, depends on the conformal structure. So,
Well, it depends how you try it. You look at the same quantity, you have lambda 1 times the area,
yeah.
divide by degree instead of divide by genus, and look at the upper bound of this variable.
Oh, I see. In terms of the asymptotic. Where you take the maximum over all.
Lambda 1 times the area divided by the degree.
Right, I see.
Look
Yeah.
at the supreme of this.
I see. It could be,
There
yeah.
should be there's a absolute upper bound, and there should be an absolute
Right,
lower bound.
right. Yeah, I mean, of course, we don't know that ratio actually has a limit in general, but yeah. So,
No, that may be better.
yeah. Right. Was there another question? Yeah.
Are there any examples of surfaces with maximizing metrics whose curvature isn't constant away from some singular points?
Whose curvature is not constant. Yeah, the Klein bottle would be
okay.
examples like that. Yeah. Well, actually, according to the theorem described here, that would be true for any odd genus. Also. Yeah. Sorry, any odd genus, right? Except one.
For your handle adding theorem, so does it also work when you add a handle to a closed non-orientable surface?
I think so, but I haven't really. Yeah, I think right. I don't think there's anything needed for the orientability. Yeah, in fact, Right. So in fact, I haven't yet posted this paper. So I would also like to include the non-orientable case. So it's a little bit, the classification is a little bit more complicated than the orientable one. But I think this handle addition part does work. Yeah. And so it should be true that yeah. So I should be able to do the existence for arbitrary non-orientable searches too. But I haven't really worked out the details of that. Yeah. But nothing I've said here uses the orientability.
Any other questions?
Yeah.
Is there analog to higher dimensional manifold like higher
Well,
torus?
So there are, in terms of upper bounds on the eigenvalue for a fixed volume, it isn't true for arbitrary metrics. On the other hand, if you restrict to a conformal class, then it is true. So you could look at a maximizing a problem in a conformal class of metrics. Now, I think that's going to be a lot harder to achieve. And I mean, these methods use some two-dimensional properties. So whether you would expect the maximizer to be a smooth metric there, I don't know. But you could pose that question. Another question is Yao and Peter Lee and Bourguignon wrote a paper where they proved an upper bound for Kähler metrics in a Kähler class, at least assuming they're algebraic. And so again, that leads to the question of whether you can achieve the maximum. And I haven't really thought about it, but that would be at least a well-posed problem.